let me introduce our first speaker. No introduction is really required for Professor Lindsay Greer of Cambridge, former head of Department of Materials Science and a partner director of the Royce Institute. Lindsay has a checkered career in terms of his affiliations. I note from his bio forward positions at Harvard. Traveled the world, this guy. Harvard, Grenoble, Vienna, Turin, and Washington. What a suite of those. And a collection of prizes, too. So, from Cambridge, 3 from TMS in the States, 4 from my own Institute of Materials, Minerals and Mining, IOM3, 2 from Japan, well, 1 from Germany, and to finish off 1 from China. So without further ado, can I introduce Lindsay, who's going to be talking to you about meteorites and magnets.
Thank you, Bernie, for that checkered introduction. I'd better get straight to the substance of the talk, which is one of those, I think we all have talks that we've given before and we modify. This is a talk I've never given before, and it's going to be a bit odd. It contains 2 enormous subjects, meteorites and magnets, which I'm fairly confident span a greater range of length scales and time scales than any other talk today. And there'll be a little topic in the middle, which is where we fit, and that is going to have a little twist in the tail of the narrative. So with that teaser, I shall get going. But the reason to be speaking today is, of course, this could be something that would assist the energy transition without the need to involve rare earth elements. Now, Dirk Raber has already been mentioned frequently today, and indeed this particular article has been mentioned frequently today. If you haven't yet come across it, please find it. A mere 680 references or something, I think. Anyway, yes, it's a major work. But let's, and Dirk will be appearing by Zoom, I think, tomorrow. But this allows me to just quote a little bit from him, which of course is making basic points about just how much of global energy consumption is associated with production of metals and the tonnage of minerals that have to be mined to achieve that. And if we focus on key things that are much growing in the modern world, wind turbines for energy generation, electric vehicles, these will feature often permanent magnets. And the highest performance permanent magnets have neodymium and other even more rare earths than that to give them higher temperature performance. And the amount of magnet in a wind turbine is about 2 tons on Dirk's diagram here. So it's a lot. And we've seen this chart already this morning, and the red stuff at the top is because it's deemed to be a high supply risk, and these are the low weight and heavy weight rare earths. And the red bands take you to renewables and e-mobility, and of course the linking point there is the permanent magnets. So this use of rare earths have many uses, but nowadays the predominant use by far is magnets. Now I'll take you away from that story back to the 1960s and none other than Louis Néel. And his group in Grenoble was looking at 50-50 iron-nickel, which of course you will realize is a very simple crystal structure, FCC. But they figured out that below a critical order disorder temperature of about 320 Celsius, it would order chemically within the FCC lattice to an L10 structure. But of course 320 degrees C is not a very high temperature for iron-nickel. The atoms are not mobile. If you waited for them to order at that temperature, the mobility would mean you could achieve it in between 2 and 10,000 years. So how to accelerate it? And they went to neutron irradiation as a way of achieving that and made some progress. They expected that this would be a good high-performance permanent magnet material, but clearly it didn't become a commercial viable thing to do. This is the ordering. So the lighter and darker shading represent iron and nickel. They're meant to be randomly assigned on the sites on the left and ordered into this layered structure on the right. You've lost your cubic symmetry. You don't, the unit cell dimensions don't deviate much from the cube. the axial ratio in the ordered form is about 1.007. So it's very, very nearly cubic, but it's not technically got that symmetry. Then we change to the world of meteorites. So it's 15, 20 years after Néel, people looking at meteorites found something new. Let me first of all make a brief remark on the history of meteorites. They have a very important part of our metallurgical story, because it was when Widmanstätten etched and saw this internal structure that it was realized that metals were crystalline after all. And two phases, one of which is T-night, which is the face-centered cubic phase. What was discovered later was that some of that T-night was not cubic but tetragonal, and showed the ordering that I was talking about before. Because it was found in meteorites, it had to be given a mineral name, and they chose the name tetratenite. And between cross polars, it shows up as nice and sparkly. And since that discovery, this has been the sort of holy grail in the magnet world, or one of them. So whatever review article you look at, and this is just one example, people will say, well, there are lots of things we could look at to achieve a permanent magnet without rare earths, but one of the things we would principally look at is, in fact, tetratenite. And so people have been trying to make it artificially. They're quoting likely values of magnetic properties, which for this talk I won't dwell on. And this is just another one of these review articles highlighting the same issue and quoting properties of the actual material measured in meteorite samples. People have been trying for decades, trying to do something less worrisome than neutron irradiation to speed up the atomic jumping. They've been doing heavy mechanical deformation, so you artificially promote the population vacancies. And it's fair to say that none of this work has actually led to tetratenite, but many attempts. This is another attempt, thinking, well, if we grew a crystal at a low enough temperature, maybe it would grow originally in the ordered structure, and it wouldn't have to order from the FCC. And one way to do that would be to grow it in a metallic glass. Well, this just about works. You get nano regions with some tetragonality. But again, that hasn't taken off as a process that would be commercially viable. Then our work was working on this iron-based system, which could in principle be a metallic glass. That was in fact what we were looking for, but evidently it's not what we found. Any metallurgist will immediately recognize primary dendrites in a eutectic matrix. We expected that there would be nothing interesting about the primary dendrites at all, but for some reason looked anyway. And here's a high-angle peak, which is split, which for the face-centered cubic structure should not be split. And it fits exactly what's expected for tetratenite, where you get the C over A ratio. If you imagine you've got now one unique axis, the C axis, and the A and B are equal, the intensity ratio of the two peaks should be 2 to 1, and the degree of split is the right magnitude. So there was some X-ray evidence for tetratenite in those dendrites. This, at first sight, would look cubic, but when you measure up closely, you realize it's a bit tetragonal. This shows classic copper gold, which shows the same type of ordering in FCC, where you can quench it to be chemically disordered. On heating, it orders and then goes through the order-disorder transition. You see something similar with our tetratenite, order crashing, and then when we cool, it does not reorder. It should reorder on cooling, and copper gold would, but nicely, in a way, that is just the same result as is found with actual meteorite samples, which also do not reorder on cooling. And there are various explanations, potentially, for why that might be so, to do with different ordering patterns developing. The critical evidence in my mind was this, that, of course, once you make it slightly tetragonal, some of the things that are forbidden reflections for FCC are no longer forbidden, and here they are, they're showing up. So that was our little story. We could not possibly claim to have characterized the magnetic properties in any serious way, but the preliminary study in the microscope shows that the tetratenite sample shows large single domain regions. This is 1 micron scale bar here, half a micron here. So this is quite substantial and quite different from the up and down domains balancing out in just a simple face-centered cubic soft magnet. And from that initial sample with very fine dendrites, we could adapt the composition and get a larger volume fraction of the dendritic phase. You could wonder, well, if we got tetratinite, why had nobody ever seen it before? Because there were lots of people looking for it. The best we could come up with on that was phosphorus. It'd been known for some time in the meteorite literature that their earlier estimates of meteorite cooling rates, which of course is degrees over millions of years, were wrong. And they were wrong because the lab experiments they'd done to simulate meteorites didn't put phosphorus in. They just looked at the iron and the nickel. And when you do put phosphorus in, it accelerates the diffusion, presumably by stabilizing vacancies. Now, that was just a 2 order of magnitude shift. Here we're showing, just from the literature and ab initio calculations, that you can get more orders of magnitude enhancement in iron-nickel systems in the presence of phosphorus. So that maybe helps us to see the ordering on a shorter length scale. So this was our paper that came out on this topic in October. It immediately attracted the attention of Bloomberg the same day, quoting Joe Biden. Now, I cannot guarantee that Joe read our paper, still less that Joe is an expert on tetratinite, but he was interested in the big strategic tussle with China over rare earth supply. And it was immediately in the next 10 days picked up by about 160 news agencies around the world. So quite a big story, not really because of tetratinite, but because of rare earths. And we've seen this chart before in some form. It's giving us an indication of cost for different elements, but the cost is not really the key thing. It's supply risk. And right at the top are the light and heavy rare earths. And the iron and nickel, of course, do not pose a supply risk. This is from Dirk Rabe's review, and it quotes the horrifying number, we've already heard it hinted at today, that the recycling rate for these rare earths is tiny. I mean, it's disgraceful. And you're having such an effort to mine them out of the earth in the first place. I should say, I'd be probably telling you something you know, rare earths are not actually that rare, but there's still a lot of very low-grade ores. And this, I think the real issue here is not the supply risk. The issue is environmental. And this is just a now out-of-use mine in China with the severe environmental degradation. This is a chart we've seen before showing the main rare earth mining in China. There's a railway going down here which takes you to this site where it's being processed and is said to be one of the worst places in the world to work, unsurprisingly. So we thought, well, if you could make tetratinite more easily, what opportunities would it bring? It might not match the ultimate performance of iron, neodymium, boron, but it might be a lot cheaper, mainly because of the processing, not so much because of the rare earth content. And this is just a chart balancing price and maximum energy product, which is your performance metric. And the tetratinite-based magnets have a potential to be roughly here, so rather lower in cost and a bit lower in performance than iron, neodymium, boron. I think the message, the take-home message from this is that there's a spectrum of magnetic materials, and the more you have, the better, because you can then pick where you might best sit on that spectrum to get the optimum performance with least environmental cost. Meteorite studies have continued, and people are coming up with property values, and they're claiming that maybe we should be thinking that the properties were even better than originally thought from meteorite samples. Now, I will have to admit that in our work we were profoundly naive in 2 ways. I had thought, well, people had said, well, we've been trying to make tetratinite the phase for decades and not succeeding. So when we see tetratinite, I sort of think, well, that's it. Problem solved. But no, not at all, not even close. Because it turns out from the meteorite world, there's the zone called the cloudy zone. It's relatively rare, has a rather special microstructure. I should say not all meteorites are iron nickel, but this is a family of meteorites. And this zone turns out to be of great interest because it has a magnetic recording ability. and you can record the magnetic history of the environment the meteorite was in, which of course is very important for that sort of studies of the origin of our universe. But you get this recording ability only in this cloudy zone, not throughout the meteorite. Why? Well, if you take meteorites that cool at different rates, or regions that cool at different rates, if it cools too slowly, the tetratinite particles are a bit big, and they therefore are not magnetic single domains, and that single domain particle size is critical to get the best performance. If your cooling is too fast, they don't have time to form the tetratinite. This reminds me to remark, why do you get tetratinite in meteorites? Well, it's thought to be just because they cool so exceedingly slowly. So although the ordering might take thousands of years, it's got millions of years to do it, so there's no problem. So that's why it was such a difficulty as foreseen. But if you're just in the right zone, you get small enough particles to be single domain that are well enough ordered to give you the magnetic properties. And the region over which that occurs is the shaded bit in the middle, which is quite broad, actually. So we then published in October. We then went ahead to thought, well, gung-ho. All we need to do now is get a higher volume fraction of the dendritic phase and optimize the properties, in particular the iron-nickel ratio, to get the best ordering. And we have a new team of people, blah, blah, blah. And we see no tetratinite. And so we think, well, we better then, having got lots of samples that don't show this phase, we better go back to those original samples and ask the question again. And it turns out that our preferred explanation of this is now that it is just an accidental coincidence of peaks of a phosphide phase. And it mimics exactly what you should get for tetratinite. But if you go to different X-ray wavelengths to be able to go up higher in the Q scale, the equivalent peaks at higher angle are not split, as they should be. So I don't think this provides us with evidence for tetratinite after all. And this I thought was our surefire thing. Well, you can see that we have a ring here, which will be some sort of deposit on the thin foil prepared for TEM. So it's a redeposition. So we went to some effort to eliminate that by cleaning up the thin foil preparation. When you clean that up, you don't get these peaks. So we come to the reluctant conclusion, having looked at it closely, that these are actually a rather weird double diffraction from the deposited nanocrystalline rings. Maybe the message here is that if it looked too easy to be true to make tetratinite by direct casting, maybe it was too easy to be true. So this brings us to conclusions, and I'm leaving us with time for some discussion. So I think despite the fact that we might not really have made tetratinite, or at least not in the quantities we thought we have highlighted the issue of composition control, in particular putting phosphorus in to speed up the diffusion. And it is clearly still an area of opportunity, because we know with absolute certainty from the meteorites that this material can exist and has good magnetic properties. So as metallurgists, we should be able to figure out a way to make it. But that hasn't yet happened. So the good properties can be achieved in iron-nickel alloys without rare earths, but it will be a very long road, I think, to get from where we are right now to having a commercial, practical magnet material. But however we're going to do it, we know it should be possible, and it's our innovative metallurgical approaches that will be needed for the sustainable production and the optimization and the recycling of the permanent magnets. Quick last comment. This, of course, has been about non-structural application magnetic. There is a structural side to this. Iron, neodymium, boron is profoundly brittle. Tetratinite is not. So there are further considerable advantages if you could make this work. Thank you very much.
Well, can I throw that interesting story start to finish out for any questions?
I'll make a comment.
It's on its way, Marty.
I joined the Naval Research Labs in '61. Al Schindler and the group I was in the metal physics group. Guess what? We were annealing the iron nickel alloys of that composition in the NRL nuclear reactor. And I had since I was sort of low man on the totem pole, I was the guy brought in for through the night watching the sample sit in the reactor for the so-called ordering reaction to take place. I learned to play the oboe during those nights. No one around to annoy, and I learned long tones. But as you pointed out, just about the point we were starting to get our results, NAOL published their paper, and I still deeply remember the day Al Schindler walked in and said, "Shut it down." and that was the end of the tetratenite activity at the Naval Research Labs. They really thought they could do it as well.
Yeah.
And I guess I am somewhat surprised at the current status. What's your feeling for the future of this ordering reaction?
I think the immediate future research-wise is doing ab initio calculations and stuff. We've done something at Cambridge with Chris Pickard looking at relative phase stabilities. There's no doubt that L10 phase is the proper stable phase. So that at least is secure. But how to get it and get it in the right microstructure, because the microstructure I showed in the meteorites a bit resembles Alnico structures, which are achieved by spinodal decomposition and took many years to develop to commercial success. So at the very best, we could hope for a timeline no shorter than that. But I just don't know how good the prospect is of accelerating that ordering through chemical means. We can do it by a few orders of magnitude, but it might not be enough, because between the meteorites and doing it in seconds in the lab is about 12 orders of magnitude.
Yeah, I think a comment from Brian. Any other questions before?
Yeah.
Yes.
What about the strong deformation? Could you eventually get a texture?
So people have tried this, and you're quite right in thinking that there may yet be prospects there. My feeling is that you may end up with a losing battle, that you generate mobility, but you're also actively disordering the system by the heavy deformation. And which one wins?
Okay.
Yeah. But that's what people have tried a lot. Yeah. And they've seen some tetragonality, but a so-called A6 phase, but not chemical ordering, which you really need for the magnetic properties. Yeah.
Okay. No other questions. A comment from Brian.
Can I get the microphone?
There's one better.
Behind me, yeah. That's the Panto, isn't it? Yeah, it's behind you. Yeah, Lindsay, I just want to make a quick comment. One of the things that which I'll talk about tomorrow, of course, is multi-component and high entropy alloys. And one of the things that whole area has taught me is, and this goes back to something you and I were talking about earlier. Alan Cottrell used to give a talk about what he used to call shocks in materials. But every so often, actually he called it shocks in metals. Every so often people discovered interesting and unusual things, whether it was quasi-crystals or metallic glasses, things that people said couldn't exist were discovered. And he never said in his talk why, but he did point out that this happened. His earliest one was actually the ductile brittle transition. So I now think I know why, having heard that talk. And the reason is that we never explored multi-component materials. Every so often, people fell over, so to speak, somewhat by accident, sometimes by inspired experimentation, whatever, or sometimes by clever theoretical thinking, a new bit of multi-component phase space where a new material existed with new properties, which, so never say never.
Yeah.
Is what the thing I have learned, I think, is never say never, because it turns out that the vast majority of materials we've never even made, and that's true particularly about metals, we've been unbelievably conservative in our alloying. And so I think there's massive prospects here. You know, prospecting is, I think, the answer. And of course, all of our thermomechanical processing tools as well. But a degree of compositional prospecting might well be worth a bit of inspired experimentation, let's call it, to be nice to.
Thank you.
Lindsay, thank you very much indeed.